specialty is geometric analysis, and she'll be telling us about entropy in mean curvature flow. All yours, Lou.
Okay, so hello everyone. So I first like to thank Mahan for his kind introduction, and it's my honor and pleasure to speak at this virtual ICM 2022. So my talk will be about entropy in mean curvature flow. Here is the outline of the talk. I will first discuss background for mean curvature flow and entropy. The entropy, it is motivated by the study of mean curvature flow. Then I will report some recent progress about sharp lower bounds on entropy. Finally, I will talk about stability questions for entropy with the emphasis on the topological perspective. So let me start with introducing the mean curvature flow. So in this talk, we'll consider family of hypersurfaces in Euclidean space. We say this family of hypersurfaces evolves on the mean curvature flow if the velocity of every point on the evolving hypersurface is given by the mean curvature of the hypersurface. At times, so we will also refer to mean curvature flow as a family of hypersurfaces on which every point is moved with the normal part of the velocity equal to the mean curvature, as the tangential part of the velocity is irrelevant to the movement of the hypersurface in this ambient Euclidean space. So the figure here illustrates a family of, it's a numerical approximation of a family of planar convex curves evolving under curve shortening flow. That is the one-dimensional mean curvature flow. It is worthwhile to point out that so the flow in general actually never attains a round circle in finite time as suggested in this numerical approximations picture. So however, the flow is indeed becoming more and more circular until it disappears in a point in finite time where it also becomes singular. So indeed, it's not hard to see that by the maximum principle, actually any mean curvature flow starting from any closed hypersurface in Euclidean space will develop singularities in finite time. So a fundamental question in the study of mean curvature flow is to understand asymptotic behavior of the flow near singularities. So to achieve this, we need to appeal to standard blow-up analysis together with other tools such as Huiskin's monotonicity formula. So at the end, by combining work of Brackey, Huiskin, and Ilmanen and White, one can show that, so if zoom in on the flow near a given singularity, so one could observe the flow look approximately like a special solution to the flow in which a later time slice is a scaled down copy of an earlier one. And such a solution is called a self-similarly shrinking solution to a mean curvature flow. And it has this form, MT is given by the rescaling of the -1 times less by the factor square root -t. And hence the flow exists for all negative times and is become distinct at t equals 0. And very often, so we will call the time t equal to -1 slash a self-shrinker. So it's known that there are actually infinitely many possibilities of these singularities models that could pretend for the flow. However, so the simplest examples are these static planes, shrinking spheres, and cylinders. So these are conjecturally the only ones arising in mean curvature flow starting from a generic closed surface. So here, generic means open and denseness. So meaning that so you can perturb any closed surface and then apply the flow to the perturbation. So the flow will develop only these spherical cylindrical singularities. Okay. So this conjecture is often attributed to Agnon, Traub, Ilmanen, as well as Huiskin. So recently, Coding and Minicozzi has pioneered a set of innovative ideas and techniques to make the most decisive progress towards this conjecture on the generic singularity in mean curvature flow. And to start off, let me introduce this functional f, which is given by this Gaussian surface integral with the centers equal to x0 and the scales equal to t0. And you can see from this formula here. So let me just mention that this Gaussian surface integral is ubiquitous in the research of mathematics, such as probability and convex geometry, as well as other scientific fields like modeling various physical phenomena. So to us, an important property of this f functional is that, so the critical points of this f functional are exactly the time t equal to minus t0 slice of self-similarly shrinking solutions to the mean curvature flow, which become extinct at t equal to 0 and at x equal to x0. So these solutions has this nice closed form here. So which means that the t times less mt, it is equal to square root minus t times this translation of time equal to -1 slash translate by minus x0 and then translate by x0. And again, so this is the solution to the flow exists for all negative times. So however, so this, if one works solely with this f functional with the fixed choice of the center and the scale, so there are several disadvantages. So for instance, so this functional f, it is not invariant under translations or dilations. And when we study this generic mean curvature flow, it's inevitable to consider family of flows. So having a quantity that is invariant under translation and dilations, it is very crucial. And also this functional f, it is not monotone under the mean curvature flow. So which is make it a little inconvenient to work with. So to rectify these disadvantages, so Coding and Minicozzi define this entropy lambda of hypersurface sigma in Euclidean space by taking the supremum over the Gaussian over the f functional with varying the center x0 and the scales t0. So then the entropy satisfies these nice properties. That is, it is invariant under the rigid motions and dilations. It is non-increasing under the mean curvature flow. And the critical points of entropy are given by self-shrinkers. With this notion of entropy, with this notion of entropy, Coding and Minicozzi went on to give a complete classification of entropy stable self-shrinkers. So that are hyperplanes, round spheres, and generalized cylinders. So the assumption on the polynomial volume growth, it is always fulfilled if the self-shrinkers arising as the singularity models of a mean curvature flow starting from a closed hypersurface, which is one of the most interesting case under consideration. Okay. So the figure here illustrates a truncated part of a complete non-compact self-shrinker in R3 of high genius and one end asymptotic to a cone. So this example was conjectured originally by Ilmanen and has been shown to exist rigorously by Kaplias, Klein, Muller, and independently Wang. So using these gluing techniques. So what's as application of Coding and Minicozzi's classification, one can find a small perturbation, though not necessarily compact, is supported of this self-shrinker shown in this figure here. So to strictly decrease the entropy, now if one apply the mean curvature flow to the perturbation and appeal to the monoticity property of entropy along the flow, it would be easy to see that. So this self-shrinker shown in this figure will not appear as a singularity model in the flow starting from the perturbation. So meaning that, so the only singularities in the flow that cannot be perturbed away are these hyperplanes, round sphere, and the generalized cylinders. So by the discussion so far, we have seen that the entropy plays an important role in the study of generic singularities from the mean curvature flow. So next, I would like to switch gears to demonstrate that the entropy is actually a very natural measure of geometric complexity. And moreover, the mean curvature flow, one can utilize mean curvature flow, in particular this classification theorem of Coding Minicozzi, to study it. Okay. So to begin with, let's take a look at the entropy for curves in plane. So it's a classical result of Amschel-Lauer that all smooth embedded self-shrinking curves in the plane are straight lines and round circles. So then if one start the flow with a simple closed smooth curve gamma, say, in a plane, then the flow will flow smoothly. And for a short amount of time, and by Grayson's result, it will eventually become convex, and its contract the curve in the plane will eventually disappear in the point. So then one can either refer to the classification of self-shrinking curves by Amschel-Lauer or by this result of Gauge-Hamilton to see that. So zoom in the flow around this point where the flow disappear, one will see this self-similarly shrinking circles appear as the blow-up limits. So that's why we call it disappears in a round point. Then it's not hard to see that, so the entropy of the initial curve gamma will be bounded below by the entropy of the flow at the singularity, which is modeled by this round circle. So hence we arrive at this nice entropy inequality, which says that entropy of the curve gamma, it is bounded below by the entropy of the round circle. So here we don't need to worry about the center or the radius of the circle, because this entropy, it is invariant under translations and dilations. And if one work carefully backwards along this inequality, then one can observe that the inequality holds if and only if the original planar curve gamma, it is a round circle. Okay. So it will be very natural to speculate analog results in higher dimension. Though the flow in higher dimension will develop various singularities. Like I showed you in the previous slides, this figure of this truncated part of the self-fixed shrinker that's actually of high genius with 1n asymptotic to the cone, right? So, and we don't expect the picture for the flow in higher dimensions as simple as in the curve case. So nonetheless, so in part suggested by the dynamic picture for this generic mean curvature flow. So together with coding Ilmanen, Minicozzi, and White make the following closely related conjectures. So the first conjecture, it is about some a sharp lower bound for a non-flight self-shrinkers that is also non-spherical. So for dimension n less than equal to 6, so there exists a positive small number epsilon, which depends only on the dimension n, so that if sigma, it is a non-flat self-shrinker in this Euclidean space of dimension n plus 1, that is not equal to the round sphere, then the entropy of this self-shrinker sigma is bounded from below by the entropy of the round sphere of dimension n plus epsilon. Then essentially appealing to this monoticity property of entropy. So if one can prove this conjecture A here, it would imply by combining with the flow to deduce the conjecture B, which is about sharp lower bound for closed hypersurface. So namely for dimension n less than equal to 6. So if M, it is a closed hypersurface in this Euclidean space of dimension n plus 1, then one can show that, one expect to show that the entropy of this closed hypersurface M is bounded from below by the entropy of round sphere. As we seen from the previous slides, so for n equal to 1, this both conjecture actually are true by earlier work. And the upper bound on the dimension is closely related to the regularity theory for minimal surface. So in which this minimum cones could also be viewed as singular self-shrinkers. So that's why when they make the conjecture, they restrict the dimension to 6. Okay. So next, I would like to report some recent progress towards these conjectures. So I will first present results about the conjecture A. So it's indeed proved in the same paper they proposed these conjectures. So coding Ilmanen and Minicozzi White show that given any n dimension n, there exists a positive number epsilon depending on n only, so that if sigma it is a closed self-shrinker that is not equal to the round sphere, then the entropy of sigma it is bounded from below by the entropy of sphere plus epsilon. Okay. So note that in their theorem, so even though the conjecture is for n less than equal to 6, but they were able to show that if one assume closeness of the self-shrinker, then this conjecture is actually true for any n, which is quite striking. And with Jacob Bernstein, we prove this conjecture A for the dimension equal to 2. So namely, one can find some positive number delta, so that if sigma it is a self-shrinking surface, and that is not equal to a plane, round sphere, or cylinder, then we show that the entropy of a self-shrinker is bounded from below by the entropy of the circle plus delta. Okay. So now let me briefly explain some idea of the proof of both theorem. So we're going to argue by contradiction. That means, so we're going to assume the entropy of the self-shrinker under consideration is small. For instance, in the closed case, it is less than the entropy of the sphere, or in the two-dimensional case, it is less than the entropy of the circle. And then we can appeal to coding Minicozzi's classification of entropy stable self-shrinkers to assume that this self-shrinker sigma under consideration are not this actually sphere, plane, or cylinder. Okay, and by their theorem, or more precisely the proof of theorem, so one can actually perturb this self-shrinker sigma, okay, to one set to produce a rescaled mean convex hypersurface sigma tuta. And the point is that such mean convexity will be preserved under this mean curvature flow. So when sigma is closed, so one can show that the flow starting from sigma tuta may develop only spherical or cylindrical singularities. Hence, the theorem of coding Ilmanen and Minicozzi White easily follow from the monoticity property of entropy. And when sigma it is non-compact surface in R3, so the flow starting from this perturbation sigma tuta may either develop cylindrical singularities or it becomes star-shaped. And if it's developing cylindrical singularities, then it's the same reasoning as the closed case that one used the monoticity property to deduce some lower bound for entropy that is contradicted to the hypothesis. Okay, and if it becomes star-shaped, then one can see the original shrinker has to be actually topological disk. Then one can appeal to this beautiful classification result of Branley, which asserts that the only genus zero self-shrinkers in R3 are planes, round sphere, or cylinders. Okay, and so then it has no choice but sigma equal to a plane. So the main issue in higher dimension for this conjecture A about this sharp lower bound entropy for this non-flat cell shrinker is the lack of this Brownlee's classification theorem in higher dimension. So Brownlee's argument relies on dimension 2 in a crucial way. So that's why that's one major issue that this conjecture A is still open in higher dimension. Now I would like to talk about some progress towards the conjecture B on the sharp lower bounds on entropy for closed hypersurface. So with Jacob-Bernstein, so we prove conjecture B is true for n less than equal to 6. And it was very surprising that Jonathan Drew was able to extend it to all dimension n. So now we have this theorem given any dimension n, and let M be a closed hypersurface in Euclidean space of dimension n plus 1, then the entropy of this closed hypersurface is at least the entropy of the round sphere of dimension n. And moreover, the equality holds if and only if M it is a round sphere. So even though I mentioned that the conjecture B, the sharp lower bounds on entropy of closed hypersurface could be implied from conjecture A about the classification of low entropy cell shrinkers, while this monoticity property for entropy. So however, so in this proof of conjecture B, we were able to find a way to get around the conjecture A. So the key observation is that, so we have this nice weak notion of solutions to this mean curvature flow. So we can actually pass the flow through singularities to construct some global weak solutions to the flow that exist through singularities, and it will disappear in finite time. So instead of looking at the first singular time, as many other people did in the study of mean curvature flow, we observed that the terminal singularities of low entropy satisfy this property we call the collapsing property. So basically says that you can't put certain size ball on either on both sides of this singularities. So then one can relate this collapsing property with this compactness property of the singularities, then eventually reduce to this theorem of calling Ilmanen Minicozzi white. Okay, so that's how we be able to get around the conjecture A to prove this conjecture B directly. Okay. Now we've seen that this round sphere minimizes entropy among all this closed hypersurface. So it will be a natural follow-up question would be to understand the stability of this round sphere under small perturbation of this entropy. So indeed, so the classification of this low entropy self-shrinking surface in R3 naturally give rise such stability, topological stability for this round sphere in R3 under small perturbation of the entropy. So namely, so if you start with a closed hypersurface, the entropy is less than the entropy of this round circle, then you can see that so the surface itself must have genus 0. Okay. So, but since we don't have a conjecture A for a higher dimension, so if we want to consider this topological stability question in higher dimension, so we need to find other ways to deal with that. So for simplicity, I will just mention this one particular result for this dimension 3. So let's consider M, it is a closed hypersurface in R4. And satisfying this entropy upper bound, namely the entropy of M is bounded from above by the entropy of 2 sphere. Okay. Recall that from the previous theorem, we see the entropy of M must be bounded from below by the entropy of a 3 sphere. And by computation of Stone, so the entropy of round spheres is monotone, strictly monotone, decreasing with the dimension. So under this upper bound assumption on entropy, so one can show that this M must be smoothly isotopic to the standard 3 sphere. This was proved by Jacob Bernstein and myself, and independently and by a completely different approach by Chodor, Mantoulidis, and Schultz. And I want to, it may be interesting to point out that, so one can view this as some 4-dimensional smooth Schoenflies conjecture in this low entropy setting. So what this 4D smooth Schoenflies conjecture asserts that, so if one has a closed bounded region, smooth region in R4, and suppose the boundary of the region is diffeomorphic to the 3 sphere, then the region itself, the closed region itself, it is diffeomorphic to the standard closed unit ball. So of course, we didn't prove this conjecture in full generality, but this theorem can be think of as this smooth Schoenflies conjecture for hypersurfaces in R4 of low entropy. So the main challenges in the proof of this topological stability result is to deal with the possible asymptotic conical singularities that appear from the flow starting from this closed hypersurface M. So in the work of Chodor, Mantoulidis, Schultz, they were able to show that one can perturb the initial hypersurface M so that the flow starting from the perturbation will only develop spherical or cylindrical singularities. Then one can easily use this monoticity to see that. So the flow starting from the perturbation plus the perturbation provide this smooth isotopy from M to this standard sphere. And with Jacob Bernstein, so we adopt a different approach. So namely, we were able to show that, so apply the flow to the original closed hypersurface M under consideration. And when the flow crossing any asymptotic conical singularity, so the isotopic class will not change. Hence one can also show that so this original hypersurface must be smoothly isotopic to this standard 3 sphere. Okay, so our approach actually led us to begin this long investigation about properties about self-expanding solutions to the mean curvature flow. So here I mentioned 2 interesting questions that arise in our approach. So the first question is about how does the mean curvature flow resolve conical singularities? And the second question is about this non-uniqueness of mean curvature flow starting from a cone. Okay. So the figure here illustrates this cross-section of this self-similarly expanding evolution coming out of a double cone. This is by Agenant, Trop, and Ilmanen. So how to generate this self-similarly expanding evolution from this cross-section? So one can first rotate around this u-axis, the y-axis, and then one can do the reflection symmetry around the u-axis. Then one gets a rotationally symmetric self-similarly expanding evolutions to the mean curvature flow. And it also has this reflexive symmetry with respect to the U axis. And from this picture, so the dotted line is the cross section of this double cone. And as you see that when you vary the aperture of the cone, one could actually either get a unique similarly expanding solutions or get multiple ones. And this is closely related to the value of the aperture. So if the aperture is large, then you get more solutions. So this non-uniqueness issue is also related to this so-called well-postness or non-fattening for this weak solutions, weak solutions to the mean curvature flow. Okay. So now let me tell you something about partial answers to these questions. Okay. So to the for the first question about the resolution of conical singularities, so we consider a situation like the cone with a smooth embedded link, and then we consider a mean curvature flow MT that exists for a short amount of time, and as time tends to 0, this flow converts to this given cone C. So under the assumption that this flow is trapped between two self-similarly expanding solutions to the flow, namely this MT plus minus is given this form, and we also assume this self-similarly expanding solutions MT plus minus also converts to this cone as time tends to 0. So then we can show that the blow-ups at the vertex of the cone are modeled by this self-similarly expanding solution to the flow. Okay. So let me just mention that this assumption here is actually very natural. So for instance, if you have this n is somehow between 2 and 6, then you can basically this condition is actually guaranteed. So it's not something artificial or yeah. So so the main idea is to find the suitable notion of monotone quantity. So but before the singular time, so this is a well-known Huiskin's monoticity formula, which says the Gaussian weighted area is monotone along the flow. So however, so when we consider the flow emerging from the singularity, so the quantity in the Huiskin's monoticity formula will become infinite. So we have to do some kind of operations analog to renormalization. So we call it this relative entropy motivated by the self-expander. Basically, we use one of these self-similarly expanding solutions as reference so that we can subtract a certain weighted quantity so that the difference become finite. So then we can work out an estimate to show this forward analog of Huiskin's monoticity formula that would easily give this blow up of the flow at the vertex of the cones modeled by these self-similarly expanding solutions. Okay, so this is the answer to question A. And for question B, so as we've seen, the non-uniqueness is inevitable, but it's an example of eigenentropy Ilmanen. So however, we observe that, so if we assume the entropy of the cone is strictly less than the entropy of the sphere of dimension n-1, then we can get this topological uniqueness theorem for this self-expanders that are asymptotic to this cone. So, so for similarly, so because it's also related to the regularity theory of a minimal surface, so we restrict the dimension n is less than or equal to 6. And when equal to 1, so everything is graphical, so one can just appeal to the result of Acker-Huisking. Okay. So here the main idea is to try to construct this Morse flow lines that connect any two self-expanders. So so I think so the details is kind of in the paper already. So I will just leave it here. Okay. So as a summary, so I hope I have convinced you that on one hand, so the entropy, it is a useful quantity in the study of singularities of a mean curvature flow. On the other hand, mean curvature flow can be used as a tool to study entropy as a natural measure of geometric complexity. Okay. So to conclude the talk, I would like to mention a couple possible future directions in the research about entropy. So it would be nice to have classification for self-shrinkers of low entropy in higher dimension, namely to prove this conjecture A of coding Ilmanen Minicozzi White, and even more generally, to try to classify this Asian solutions to mean curvature flow of low entropy. So self-shrinkers, as shown in the definition, are special class of solutions to mean curvature flow that exists for all time, negative times. So it would be nice to have this classification of self-shrinkers of low entropy generalized to all the Asian solutions. And for interested audience, one could refer to, for instance, this very nice paper of Troy, Hasselhofer, Hershkovich, and reference therein. And it was also natural to consider this sharp lower bounds on entropy for submanifolds of any codimension. In this direction, so Coding and Minicozzi made some initial important progress, but there's still a lot of open questions that I found this natural and interesting. And I think I would like to end my talk here. And thank you for your attention. And I guess if you have questions, I'll be available after talk to answer on the Discord. Thank you.
Yeah. Thank you so much, Lou, for this beautiful and very clear talk on low bounds on entropy and topological stability, and the striking thing about the four-dimensional Smoot-Schoenflies conjecture in the low entropy setting. Thank you very much. And as Lou has already pointed out, audience is welcome to ask questions on Discord. So thank you again, Lou, for this lovely talk. Yeah.
Thank you. Thank you for having me. Bye-bye.